so quizzes. The one that was due yesterday was 6.2, right? All right, which one were we talking about?
6.
Number 6. Approximately what proportion of babies will have birth weights between 6 and 8 pounds? And it gives you the mean and the standard deviation. So this is an in-between probability. So that means we're going to need 2 z-scores and 2 probabilities. So I'll just bring it up here. So here, first, we would do, so there's basically 2 cutoffs, 6 and 8. I made this a little thinner. All right, so you have this, there's a normal distribution then. You know, it's centered at 6.8. And then I'm looking for what proportion will be between like 6 pounds and 8 pounds. So I'm looking for an in-between probability. In-between probabilities require 2 z-scores and 2 probabilities. So you'd get your first z-score by taking, so for we could do the top one, say 8. So it's observation minus the mean divided by the standard deviation. So that would give you your top z-score, and I don't remember what that comes out to be. Does anybody remember or have it? I can calculate, or could you calculate it for me real quick? I did it earlier this morning for somebody else. What is it, 0.71? Or am I getting that wrong?
Wait, what?
I got 0.71. Did I get that? Is that right?
Oh, yeah, if you're round, yeah.
Yeah, you got to round it to, z-scores are always rounded to 2 decimal places because that's what the table reads. Okay, so that's 1 z-score. Then you have to go get your other z-score, so that'd be 6 minus 6.8 all over 1.7. So this one's going to be negative, and what does that one come out to be?
0.47?
Yeah, negative 0.47. Okay? Okay, so those aren't the probabilities, though. Those are the z-scores. So we need to take those z-scores to the z-table, and we'll get our probabilities off the table at that point. Sometimes it can be confusing because if your z-scores come out to like decimals between 0 and 1, it's tempting to want to stop there and treat them like probabilities. But these aren't probabilities, they're z-scores. So then we need to go to the z-table and look up. So first we'll look up like 0.71. So that would be 0.71. So the probability below 0.71 is 0.7611. You find that on your table? 0.7611. Okay, so that's the top probability here. So then to get this, we get the probability below the biggest z-score, and then we have to go look up the negative z-score. So we look up negative 0.47, negative 0.401, 1, 2, 3, 4, 5, 6, 7. It's right here. It's 0.3192 is the probability below the lower z-score. 0.3192, and then we subtract them. And then whatever that comes out to be should be the correct answer. What does that come out to be?
0.4419.
0.4419? Yeah. Like that. Question, Dustin?
I think I just didn't know where to stop rounding for the z-score. I think that's what threw me out.
Okay. Yeah. So z-scores should always go 2 decimal places because that's what the table reads. And then if you end up with, just make sure you remember where you are in the process because it's like a 3-step process. There's z-scores, then there's the z-table that gives you probabilities, and then you work with the probabilities. So it can be confusing when the z-scores are less than 1 because sometimes they seem like they should be probabilities, but they're not. So, okay. Any other questions for the quiz? Mm-hmm. So let's go back. We were here. Number 4. This is a similar one, but you have to be careful because you have to remember that this is a greater than question. Let me pull that up here. So it gives us the distribution. It says that they have a normal distribution centered at 501. And then my question is, what's the probability that someone scores more than 600? So it'd be like up here. Okay. So first we would go get the z-score for someone with a score of 600. So it'd be like 600 minus 501, and then you divide by the standard deviation. So then if you do that, I think the z-score should be, yeah, if you round, it's 1.16. It's always rounded to 2 decimal places. Okay, so we're going to have to go to the z-table to get our probability. So we need to go look up 1.16 on the table. Now if you look up 1.16 on the table, the probability below that, here's 1.16. The probability below that is 0.8770. But you have to remember that the table is always reading probability below. So then to get above probabilities, that's when we do the 1 minus. And so then you'd get the answer here was 0.1230. When you do 1 minus the probability. Okay. All right. This is on the z-table. Yeah? Any other questions? No?
You can say anything for the next one.
Probably. Yeah. It's just that in this one, so this college says that they'll only accept students who get a 550. So the ones that will not qualify are going to be below that. So essentially, it's the same. It's just you're doing the probability below 550.
You do 550 minus 501 over 85.
Yeah. That gives you the z-score. In this case, since it's a below probability, though, the probability you pull off the table will be the right answer. You won't have to do 1 minus. You only do 1 minus when you're doing an above probability.
The ones that agree today?
Yeah. Mm-hmm. Yeah, that's right. All right. Any other questions? Okay. So yesterday, I had showed you some graphs and showed you some sampling data. But mostly what I was trying to get to is I was trying to get to the point where we could see what's called the central limit theorem in action. And we were talking about looking at sample means. And what we looked at yesterday, and you can go back and watch the video if you weren't here, but is I took some data from the class. Everyone told me how many siblings they had. And then I pretended like what would happen if someone didn't actually know the true population data. All they could do was come in and sample a few people. And they could guess the average age by sampling a few people and averaging their numbers of siblings, but they would never actually know the truth. And so what I did is we did some simulations where we let the computer run a lot of samples. And what we saw is we saw that if you sample people from a population and you average them out, those averages, they're usually pretty close to the truth, and they have an almost normal distribution. In fact, the more samples you take, the closer you'll be to the truth, and the more bell-shaped your data will be. So that result is what's called the central limit theorem, and I'll just rewrite it here. You probably wrote it yesterday if you were here, but the idea was that if you have large enough sample sizes, so for large enough sample sizes, then the sampling distribution, that means the shape, the center, the spread, the sampling distribution of x bar, which is the sample mean, it will be approximately normal. So, it's not going to be, we didn't see exactly bell-shaped, but it's pretty close. Approximately normal. Normal distributions have to have a mean and a standard deviation. So the mean of the sample means would be the true mean, and the standard deviation of the sample means would be the standard deviation. We noticed in our graphs that as you took more samples, the variance got smaller, and that's true here. The variability will go down by a factor of root n. So this was the result I spent a little bit of time talking about yesterday, but really the more important thing is understanding how to use it. So I'm going to show you some examples about when the central limit theorem applies and how to use it. There's some vagueness here, right? Because this is not entirely clear, like what exactly that means. In our example, we had a pretty small population, so we didn't have to take like super large samples to start seeing really good results. But in a really big population, large enough can be sort of subjective. So typically speaking, there's a sample size restriction. So for the central limit theorem to apply for the sample mean, there's two possibilities. So one possibility is you might have a population that's already normally distributed. Okay, so if your population already has a distribution that's normal or bell-shaped, then there's really no restriction. Okay, because you're already working with a normal distribution, so you don't have to take extra sample sizes to realize a normal distribution, because the whole population itself has a normal distribution. So, in other words, we're calculating means, so you have to have at least two observations. But if the population is normal, then you don't really need to worry about sample size. Normal populations aren't that common, though. So if your population is non-normal, like the one we saw with siblings, we didn't really have a normal distribution there, then typically speaking, they're usually, by the time you take about 30 people and you average them out, you see that normal distribution start to emerge. And that's not like some theoretical result. That's just that's empirical. That's just empirically observed over a lot of data sets. Yeah.
Is that n equals 2 or
Great. This greater than or equal to
greater? Is it 2 or 1?
2. Yeah, because you have to have at least 2 people to average them. But yeah. So okay. So you just have to be. So basically, the idea is everything that we do from this point on, it takes advantage of the fact that big enough sample sizes produce normal distributions. So if you look at any sort of study and they have really small sample sizes, you just have to be really careful about how to interpret those results, because all of this is sort of hinging on the fact that you've taken enough people to see that bell shape start to take place. All right. Anyways, so let's look at how this result would be used, because it looks confusing in some ways. So here you go. So, for example, we had looked at previously selecting one person from a normal distribution. So like this right here is a module 6 problem. This isn't a central limit theorem problem. So this one is just like the quiz you took. So if the heights of women are known to have this normal distribution with a mean of 64, standard deviation 3.2. If you randomly pick one woman, what's the probability that her height will exceed 66, right? So in this case, what do you got? You got a normal distribution centered at 64. Okay, 66 is above average, and we want to know the probability that she would exceed that. So just like the quiz you took yesterday, how do you solve this problem? What do you got to do?
Find the z-score.
Z-score first, right? So 66 minus 64 over 3.2. And what does that come out to be if you calculate that and round it to two decimal places? 0.63. Other people get that?
Yeah.
Okay. So that's the z-score. So what do we do with that z-score? We take it to the z-table. Okay. And we look up 0.63 on the z-table. And if you look up 0.63 on the z-table, what's the probability of being below that?
0.7357.
Yeah, 0.7357. Of course, we didn't want to know the probability of being below. We wanted to know the probability of being above. So what do we have to do? Yeah, we'll just do 1 minus that. It's always 1 minus when you're doing a top-tail probability. And so that you do 1 minus that with a 2, 6, 4, 3. There you go. Okay. That was a Module 6 problem. So that's just like what you guys had to turn in by yesterday. If you don't have z-tables, and you want one, there's a bunch right here. Grab one if you want. All right. So any questions on that one? Is that one pretty straightforward? Okay with that? Okay. So now what happens, so typically when we're sampling, we're not just picking like one person though, right? That wouldn't make much sense to just sample one person. You would want to sample as many as possible. So let's say instead, what if we randomly selected 15 women? Now, in this case, the population, right, here, the population is already normal. So the central limit theorem applies no matter what. Okay, because I mentioned that sample size check, but if you already have a normal distribution, you don't have to worry about a sample size. So 15 is going to be fine. Now, if we selected 15 women and we averaged out their heights, what's the probability that their average would exceed 66? Now, one single woman is relatively likely to be more than 66 inches tall, right? That's like 26% of the population. Would you expect the average of 15 women to be more than 66? Do you think that would be more likely or less likely than a single person being more than 66 inches?
More likely.
Maybe more likely. What do you think? More likely? Why?
Because there's more people that could be taller than 66.
You're taking more people, but when you randomly select people, you probably will catch some tall women in that sample, but what are you also going to catch? You're also probably going to catch shorter women in that sample too. And what's going to happen to the tall women when you average them out with the short women? It's going to bring it back towards the average. So let's see. We can figure it out though. And the central limit theorem will help us figure it out. So in our distribution here, centered at 64, and then now we're at 66. Okay. So the process is still exactly the same. But what we have to remember is that the central limit theorem told us that the mean of the sample means will be centered around the true mean. So the center doesn't change. We saw that in our graphs yesterday. It was always centered around the same number no matter what. What changes, though? What changes is the standard deviation. And the standard deviation is going to decrease because we're averaging out multiple observations. So you might get some tall people, but you're also going to get some short people, and they're going to average each other out and bring them back to center. You're not going to get as much spread. It'd be really, really weird to randomly select 15 women and just happen to end up with 15 really tall women. It's not going to happen very often. Same with 15 very short women. You're going to get a mix. So the standard deviation, the population standard deviation was 3.2 inches, but that's now going to decrease by a factor of root 15, according to the central limit theorem. Okay. So what we have to do here is we have an updated standard deviation. And so we need to update our standard deviation to take into account the fact that we sampled and averaged multiple people. So if you do that, do 3.2 divided by the square root of 15. What do you get? Maybe give me like 4 decimal places or something. 8262? So it was 0.8262? Okay. So that is going to be your new standard deviation. So the problem is going to be solved exactly the same way. We're still going to calculate a z-score, but our denominator is going to change. And so what I just have an updated z-score formula, basically. Whereas this, I'm going to write the original one. Okay. So really, yeah, actually I will write it this way. Really what we're doing is our cutoff is a sample mean. We want to use the mean of the sample means, and we want to use the standard deviations of the sample means. So the form is still the same, but we can sub in our central limit theorem values, and essentially we get an updated z-score formula that we can use to calculate probabilities like this. when we average out multiple observations. So if you're sampling one person from a normal distribution, that's like the problem before, and it's your standard z-score formula. If you're sampling multiple people and you're averaging them out, it's the same process, but we're going to use this updated z-score formula. So it'll look almost the same. You know, we're still going to do 66 minus 64 on top, but what's going to change is on the bottom, we're going to use that updated standard deviation, that smaller standard deviation that takes into account averaging multiple people. So if you do that, what's the z-score for this problem?
2.42.
2.42? Other people get that? 2.42. So it's 2.42. So if we take that to the z table, you know, 2.42 is out here. We're looking probability above. If you look up 2.42 in your table, what's the probability below?
0.9922.
Yeah, it's 9922, which means the probability above that is very small. It's like 0.0078. So. Yeah.
So we'll use this anytime we have more than, or 2 or more observations.
Yeah, anytime you're averaging 2 or more observations, you'd be using the updated z-score formula.
And is the top always going to stay the same?
Yeah, the mean doesn't change because in the central limit theorem tells us that the means are the same. The mean doesn't change at all. The only thing that actually really changes is that standard deviation. So it's going to decrease. Okay. So what happened was, it's like, here, I'm going to insert a slide here. See, one woman was relatively likely to be greater than 66 inches tall. But 15 women averaged out. It's not very likely that that average will exceed that. And the reason why, it's because of the graphs we saw yesterday. So like in red here, this might be what the population looks like, right? So like red is your population. That's what the heights actually look like. But what happened yesterday when we took multiple samples, let's say like x bar if n equals 15, what did we see in our graphs yesterday? What happened to the distribution? It's like everybody started to do what? Everybody started to pile up, right? Around the middle. Okay? And so what happens is that then in the calculation we just did, you know, maybe here, maybe 66 inches is right here, right? So what you can see is that on the red distribution, you know, in the overall population, it's pretty common for a woman to be more than 66 inches tall. But among the average with n equals 15, what happens there? What do you see happens? The average almost never makes it out that far. Because when you average out people, the tall people and the short people bring each other back to center. And your means are going to be all piled up right around the true mean. You know, it's just not as common to see means out there. It happens. It could happen. It's just not going to happen very often. It's very unlikely. So, does that kind of make sense? Okay. All right, any questions about this one? All right, so the key is if you're taking one person from a normal population, you just use the old school z-score formula. If you're taking multiple people and averaging them, you need to update your z-score formula for that updated standard deviation. So, all right, here's another one. So you don't have to work with normal distributions. So like wait times at drive-thrus tend to have non-normal distributions. So let's say that at a particular restaurant that their mean wait time is 125 seconds, the standard deviation is 43 seconds. Let's say a manager randomly observes 40 orders. What's the probability that the average order time of those 40 orders will be less than 2 minutes. Okay. So like here, we can see what's going on is our sample size has gone up. And what are we looking at? We're looking at averages, right? So we're averaging multiple observations. So this is a central limit theorem problem. Okay. So as long as though our sample size is 30 or more, in this case we should check because we specifically said that the population was non-normal. So that's why it's important that the sample size was big enough, right? You want to have 30 or more if you're drawing from a non-normal population. But even so, as long as we're taking enough observations here, we're going to be in good shape. So then it looks almost identical to a Module 6 problem. You know, the mean is 125. What is 2 minutes? How many seconds is that? Yeah, we need to convert that into seconds just so it's on the same scale as the measurement system here. So then, 120 is somewhere below average, right? And then we're looking for the probability that the average goes less than 2 minutes. Okay. Problem works exactly like before. The only difference is we're going to use our updated z-score formula. So we're still going to do like 120 minus 125, but in our denominator, we're going to take that standard deviation of 43 and we're going to divide it by root 40 before we divide the whole thing. So we need to update our denominator. You could do it actually. Your calculator. If you put the numerator and the denominator in parentheses, it should figure it out. Just close your parentheses on your denominator, or you can do it in 2 steps. You can calculate that denominator first. Just keep like 4 or 5 decimal places, and then in the next step you can do it. So what does that z-score come out to be? Negative 0.74. Anybody else gets that or something similar or different? .74. That sounds right to me, or reasonable. Somebody else want to calculate that z-score for me? No? If you have to, you can do the denominator and numerator separately. But it's easier just to plug it in all at once if you can. Anybody else get something different or the same as negative 0.74? I trust you. I want to make sure. I don't have my calculator on me right now that does parentheses and stuff. All I got is my phone. Okay. Any other answers or same answers? So again, in your calculator, you can do it all at once, but you need to be really careful. You got to use your parentheses because otherwise it's going to get everything out of order. You got to make sure that you have parentheses around your whole denominator. And if your square root function has a parenthesis function you need, it should be 2 parentheses at the end of that statement. Like parenthesis. So I think that's right. But I don't. No, I want to see if anybody. I want at least somebody else to get a number. Are you guys getting totally different numbers? Is that what's happening?
Yeah.
Adding square roots in the answer.
It's just not converting.
Oh, you just go the back and forth button on down at the bottom near your enter. Just hit the back and forth arrows. There should be a little symbol on your calculator that looks like this. Like the arrows back and forth. Or it's like S to D or something like that. Yeah, there's like an S to D button or something. And then it converts it into a decimal.
Negative 0.736.
Yeah. Okay. Anybody else? You guys got to be able to get this number. Okay? If you can't get that number, you're going to have a bad time. Because, like, we got to be, it's important to be able to use our, you got to be able to get these numbers out of your calculator, even if you have to do it in multi-steps. So, you should be able to turn this calculation into negative 0.74 on your calculator. That's the right, that's the z-score looks like. Okay? Okay, so that was fun, but that's only half the battle there. Now, what do we have to do? What do we need to do? We need to take that z-score, and we need to take it to the z-table. And we just got to look. So now we got to look up negative 0.74 on our z-table. And then this one's probability below, so it's going to come straight off the table. So if you go to the negative side of your table, negative 0.74, what's the area down there? 0.2296. All right. All right. What questions do you have about that?
I'm still kind of lost behind that negative 0.7.
Well,
Could I do it when I get like 6.7?
I think you're missing some parentheses, probably. Does your statement end in two parentheses? Do you have two parentheses at the end of your calculator thing? Because, see, a lot of calculators, if you're trying to put the square root in at the bottom, it's usually like square root with a parenthesis. So you have to close the parentheses for the square root, but then you also have to close the parentheses for the denominator. Yeah?
Yeah, and then you have to do a two-step problem. You got to do 120 minus 5.
Yeah.
And then you get negative 5, and then you do the...
Yeah, the other option is you can do it in steps. 120 minus 125 is negative 5. And then you can do 43 divided by the square root of 40 in your calculator, or what does that come out to be?
6.7.
Negative 0.4.
6 point what?
7, yeah. 798.
Something.
Yes.
Yeah. Yeah, so you could do the denominator separately from the numerator, and then you could do the division. 5 divided by 6.798, and that'll get you back to the right answer too. So. Yeah, because it's like 0.736. Yeah. Okay. All right. Any other questions on this one? Okay. So it's really not any different than Module 6. We're just using the updated z-score formula. If you can figure out how to calculate it in one step in your calculator, you're going to have an easier time because then you don't risk rounding errors and stuff like that. So it's easier if you can calculate it all at once. So, all right. Here's another one. So same idea, but in this case, let's say so they're doing 40 orders. We're looking at an average. What's the probability they'll be between 110 and 130? Okay. And I'm wondering if I did this right. I hope I did. So 125 is like right here. Then 110 would be somewhere below. 130 somewhere above. Oh, not that far above. 130. And then we're looking for an in-between probability. How do we do in-between probabilities? Yep. 2 z-scores. And then 2 probabilities. And then we subtract. Okay.
So do you use the new equation?
Yes. So the numerators are the same, right? It's still like 130 minus 125. But down below, see, remember we have an n now. N is 40. We're taking averages. And so we need to take that standard deviation and divide it by root 40. And we need to update our standard deviation. So that'll be 1 z-score. And then we have a below z-score. Oh, that was cool. No, don't do that. It's because I'm getting into the menu down here, sorry. Should be 43 divided by root 40 for that z-score. Okay, so what do you get for the top z-score?
0.74. It's just like
Yeah, it's the flip of the other one, right? Because this is 5 above. So this will come out to a positive 0.74. What about the bottom one?
Negative 2.21.
Negative 2.21? Yeah. So using those formulas, this is this denominator is the same as that one. It's 43 over root 40. 43 over root 40. I just ran out of room down there at the bottom. But, right, because this is the mean. This is the standard deviation. This is your n. Yeah. Okay. All right. So then you have two z-scores. Now we can head over to the z-table. And then we know that to find in-between probabilities, we just need to look up 0.74. That'll give us a probability. We'll look up negative 2.21. That'll give us a probability. And then we can get the in-between probabilities by subtracting. So 0.74, go look it up. What do you get? 0. I get 7704. Okay. Go look up negative 2.21 in your table. Looks like it's 136. Yep. And then if you subtract those, what do you get?
0.7568.
All right. Any questions about that? Questions about where any of those numbers came from? Why we did any of that stuff? Okay. So the distinction here is basically everything in statistics comes back to the normal distribution. So far what we've learned then is, so in one case, if you're just sampling, so if it's just one observation from a normal distribution, okay, then that's a module 6 problem, and we're just going with our original z-score formula, right? Okay. If instead what you're doing, if you're taking in observations, so more than one observation, and you're calculating a sample average or sample mean, okay, so you're taking multiple people and you're averaging them out. First thing, what you want to do is you want to check, well, really, there's those two conditions, right, on the sample size. Okay, so really I'll just split it in half, because as long as the population is normal, or you have at least 30 observations, then you can go on and use the central limit theorem, right? You just have to make sure that you update your denominator because you average multiple observations. But if you have a situation where the population is non-normal and your n is less than 30, then at that point the central limit theorem does not apply. You really can't do any of this stuff. Okay. So one observation from a normal distribution, no problem. That's where we started with the normal distribution with z-table. If you're taking multiple observations and you're averaging them, that's fine as long as the population is normal or your sample size is big enough. You just use the updated z-score formula. If the population is not normal and it's a small sample size, then you're in trouble. Don't do that. The central limit theorem doesn't apply there. You can't use the z-table. You can't use that normal distribution assumption. So, okay. All right. Yeah? So really, Module 7 is just one additional little formula here. That's this right here. And really, that's the only formula you'll need, along with knowing the sample size restrictions. That's really all you'll need to take that Module 7 quiz. I don't think it'll be too tough. It'd actually probably be better if you took it sooner rather than later, since you just got finished doing all the z-table stuff from the Module 6 quiz. So I'd probably go ahead and take a shot at the Module 7 quiz. Okay? All right, any questions about that? About Module 7? Okay, I don't really want to start Module 8 today, so we're going to do that tomorrow. So, maybe go take your first attempt at your Module 7 quiz, and then you can come back and ask questions tomorrow if it's giving you any trouble. That'd be a good use of your time.